Good morning, chemistry students. This is Mrs. Krumschreider, and today we're going to be doing our Chapter 7 Day 2 notes. We're going to be starting at the number of particles in a mole on your outline and finishing Chapter 7, Section 1. Today, you're going to find out more specifically what a mole is and how many pieces it represents. Okay, and we're going to do a couple problems involving the mole. So just as a quick review, remember that we talked about the fact that there were 3 ways to measure matter on our notes the other day. We said that we could count. For example, we count matter when we count how many people are in a classroom, how many desks there are in a room, how many pencils we have. Another way that we can measure matter is we can measure matter by mass. Okay. Again, we do this when we buy our meat because we pay for our meat by mass. We do this when we sometimes buy bulk candy, sometimes nuts and things of that nature. And lastly, we can measure matter by volume. Again, we do this when we buy gasoline, we buy a gallon of milk or a half a gallon of apple cider. Okay, so again, keep in mind that as we talk about a mole, eventually we're going to see that we can use a mole as a count, as a mass, and as a volume. So you want to kind of keep these 3 ways that we can measure matter sort of in the back of your head as we work through talking about a mole and how we use a mole in chemistry. So we're going to start by talking specifically now about the mole and the number of particles in a mole. Remember, we kind of talked again the other day about the fact that there are certain numbers that are words that indicate a particular number. For example, when we say a pair, we mean 2. When we talk about a dozen, we know we're talking about 12. If we talk about a baker's dozen, we know we're talking about 13. As a chemistry student, you're going to discover that a mole is going to represent a specific number of particles as well. And you already saw that a little bit on one of your chem quests. So know that we're talking about moles because matter, which basically is everything you see in the world around you, as well as the things you don't see, like the air, is also made up of matter. Okay, matter is made of atoms, molecules, and ions. And all of these are much smaller than apples, because if you remember, and just up above this in your outline, right, we did that factor label method review and we figured out how many seeds were in 14 kilograms of apples. Okay, remember, we can see apples, we can see seeds, we cannot see atoms, molecules, or ions with our naked eye. What that means is that counting particles one by one is not practical. So basically what we're saying here is we couldn't possibly, okay, if we had like a pile of atoms large enough that it's about the size of a computer mouse, okay, it wouldn't be practical to count individually how many atoms there are. Number 1, you can't see them, okay? Number 2, the number would be extraordinarily large, okay? So we certainly can't count those one by one. So we use a mole in chemistry, and a mole of a substance is 6.022 times 10 to the 23rd power representative particles, and we're going to talk about what representative particles mean in just a minute, of the substance. And the mole is the SI unit. Remember when we talk about SI, we're talking about Le Système International de Unité, so that international system of units that all scientists and all chemists know all around the world, okay? So the mole is the SI unit of measuring the amount of substance okay, so it's the way chemists around the world talk about how much of a substance they have. Now that's 6.022 times 10 to the 23rd. That number has a special name. It's called Avogadro's number. For some reason, usually people think of the word avocado. Okay, it's Avogadro. That is a scientist, Italian scientist's last name. Okay, so Avogadro's number is the number of representative particles in a mole. Okay, Avogadro's number is the 6.022 times 10 to the 23rd power. Okay, so this is Avogadro's number, 6.022 times 10 to the 23rd, which is how many representative particles of a substance are in 1 mole of a substance. And again, we saw this number on the Chem Quest you did the other day, where you started with the atomic mass in AMUs, and you figured out how many atoms that was, and then you figured out how many particles or atoms there would be in this many grams, the average atomic mass from the periodic table. Okay, so you kind of worked with these numbers the other day on your Chem Quest. So, what do we mean by representative particle? We use the term representative particle because it's generic. So, it refers to the species present in a substance. And a substance is just something that's pure. Okay. So we have actually talked about substances before. We just haven't necessarily called it a substance. Okay. There are 3 substances that we've talked about. We have talked about an element. We have talked about molecular compounds. And now, right, I should have you on the right track to think about what that 3rd substance is that we've talked about, which were ionic compounds. Now, just as a kind of review, okay, because we're going to be dealing with molecular and ionic compounds a lot as we finish up Chemistry 1B. So, what I want you to think about is, how do you know a substance is a molecular compound? What's your test, if you will? Remember, a molecular compound is made of 2 non-metals. And remember, our non-metals, on our periodic table, there's that heavy stair-step line. And our non-metals are to the right and above that heavy stair-step line. Okay, so molecular compounds, remember, they're made of 2 non-metals. When we see a name for molecular compounds, they're going to have prefixes on them. And remember, to write the formula, our prefixes become our subscripts. Okay, and if we're naming them, our subscripts become our prefixes. And the second element ends in "ide." All right? How do we identify ionic compounds then? How do we know that a substance is an ionic compound? Hopefully you said that it's made of a metal and a nonmetal, or it has a polyatomic ion in it. So again, nonmetals to the right and above that heavy stair-step line. Everything to the left and below that heavy stair-step line is a metal. Polyatomic ions, remember there are the 10 of them you have memorized. And you should have a sheet that has those 10 listed on it somewhere. And then you also have that helper sheet, okay, that in the middle of it, remember, it has a bunch of polyatomic ions on it for you. Okay, so our three substances are an element, a molecular compound, and an ionic compound. So when we talk about representative particle, when we've talked about this before, we've said our representative particle was our smallest piece. That we could chop it up into, if we had a big chunk of it, that still has all the same properties. So we have talked about representative particles before. We just didn't necessarily call them representative particle. I would talk about if we had a big chunk of this substance. So if we have a big chunk of element and we want to chop it up into smaller pieces, and we want those smaller pieces to still have all the same properties of that element, remember that smallest piece is called an atom. So the representative particle of an element is an atom. All right, and again, if I have a chunk of molecular compound and I want to chop it up into smaller pieces so that every piece still has all the properties of that molecular compound, that smallest piece would be called a molecule. And remember, we abbreviated molecule MOLC. Now we understand why we have to have that C on there, because mole, MOL, is the abbreviation for our SI unit for the amount of substance. And again, if I have a big chunk of ionic compound and I want to chop it up into smaller pieces so that all of those pieces still have the same properties as that ionic compound, that smallest piece I'm going to chop it up into is called a formula unit. And remember, our abbreviation for this one was everyone's favorite because it was an FU. Okay, so representative particle, just we're talking about that smallest piece. Okay, our smallest piece of an element is an atom. Our smallest piece of a molecular compound is a molecule. Our smallest piece of an ionic compound is a formula unit. The mole allows chemists to count the number of representative particles in a substance. So having a mole allows us to figure out how many either atoms, molecules, or formula units we have in that substance. Keep in mind that you have some diatomic molecules that you have memorized. Okay, remember those diatomic molecules are hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Okay, there are 7 of them. And remember, on your polyatomic ion quizzes, the last question is typically to list the 7 diatomic molecules you have memorized, and these are them, right? This is Brinkelhoff. These are the posters that were up around my room with Mr. and Dr. Brinkelhoff, okay? Brinkelhoff is a way to help you remember them. And what's important about these diatomic molecules is that although these are elements, they always exist as diatomic molecules. So you're never going to see a hydrogen atom all by itself. A hydrogen atom is always going to be bonded to another hydrogen atom, making it a diatomic molecule. So the representative particle of these elements is actually a molecule, because they're 2 atoms bonded to each other with a molecular bond, or a molecular bond where they're sharing electrons. And so, although these are technically often called elements, their representative particle is a molecule. So, we now have our first conversion factor. And one of the things that I would normally do if I was in class is I would give you an index card at this point. And I would ask you to call that index card your chemistry toolkit. So if you have an index card, that's great. I would suggest you grab one out right now. You can pause the video if you need time to go find one. If you don't have an index card, then what you can do is just take a little piece of paper and, again, make it about index card size, because this is going to be called your chemistry toolkit. And as we're going to start to do problems here in the next couple minutes. As you start to do problems, one of the things that I found over the years of teaching chemistry is that sometimes people struggle to decide which conversion factor to use. And sometimes, a lot of times, it's easier to decide what conversion factor to use when you have them all sitting right in front of you. Just like the analogy I typically make is just like building a house, okay, or building a birdhouse. If you have screws and a screwdriver and nails and a hammer, by looking at the screw, you can probably figure out that you should use the tool of a screwdriver. And by looking at a nail, you can probably figure out that you're going to use the tool of a hammer. Chemistry is going to be the same way with this. Sometimes looking at your problem and then looking at your choices of tools or conversion factors to use, sometimes by looking at all of them together, you can decide which tool or which conversion factor you're going to use. So I'd really encourage you to find, again, an index card or a little piece of paper about the size of an index card that you're going to keep track of. And on that index card, besides writing this in your notes, so write it in your notes first and then copy it over to your index card, you're going to put this conversion factor. Okay, this is our count conversion factor. Because remember, we talked about there were 3 ways to measure matter. We can count, mass, and volume. And we're going to have a mole conversion factor for all 3 of these areas. This one that we're going to talk about right now, okay, is our conversion factor that we're going to use for counting. And we kind of have a generic conversion factor, and you're welcome to put the generic one if you'd like on your index card, which says that 1 mole of substance. Remember, conversion factors look like ratios, okay, or fractions. okay, is 6.022 times 10 to the 23rd representative particles. Now again, remember, the power of a conversion factor is that I can flip it depending upon where I need my units to be. Because again, we're going to start to solve problems where we're going to treat moles of substance and representative particles like they are algebraic letters that we want to cross out. So all of these, this is this generic one. And by generic, what I mean is, if you remember this, okay, chart here, you can just remember this one conversion factor. However, what I have found is most people prefer to write the specific conversion factors. So this is this generic one, but there are specific ones. Now, for the specific ones, I'm not going to write them both ways. I'm just going to write them one way, probably like this, okay, and expect you to recognize that you could flip the units depending upon where you need them to be. Now, the specific ones relate to those three different kinds of substances. So there are going to be three of them because there are three different kinds of substances. So I can have 1 mole of element, which is Avogadro's number. And now, instead of representative particle, I'm going to have what that representative particle is, which is atoms, right? For an element, the representative particle is atoms. So that's one of my 3 specific conversion factors. And again, I could also write this as 6.022 times 10 to the 23rd atoms over 1 mole of element, okay? The second one, right, another one of our substances is 1 mole of molecular compound over Avogadro's number again. Now, this time, what's our representative particle going to be? Molecules, right, our MOLC, our molecules. Again, I could flip this if I need to, depending on where I need my units to be, right? And our third substance was ionic compound. So 1 mole of ionic compound over Avogadro's number again. This time, our representative unit, remember, is a formula unit. So, what most people choose to put on their index card are these 3 specific, okay, tools rather than the generic one. Because this way you don't have to remember what those 3 substances are. So again, if you need some time to find an index card, okay, or get a piece of paper, a little sheet of paper ready, that's fine. But again, 22 years of teaching chemistry, ladies and gentlemen, I'm telling you that I really think you need to make yourself a chemistry toolkit. And these are the first 3 tools you're going to have on your chemistry toolkit. You're going to end up with 5 tools. Okay? So next we want to take a look at a problem. And here is our problem in words, because these typically are going to be story problems. So magnesium is a light metal used in the manufacture of aircraft, automobile wheels, tools. How many moles of magnesium is 1.25 times 10 to the 23rd atoms of magnesium? So again, as I've mentioned before, I don't particularly like story problems. Most of the students I have in chemistry don't like story problems. So I like to read my story problem and kind of summarize what it's asking me to do. So this problem is asking me to take 1.25 times 10 to the 23rd atoms of magnesium and figure out, so that's my question mark, what I don't know, okay, how many moles of magnesium that is. Now, this is where you look at your chemistry toolkit, because the question is, do I have a tool, okay, that has atoms and moles in it, right? And I do. It's right here. Now, to use that tool, it has to be an element. So notice, I do have an element here. It's magnesium. So I'm able to use that tool. So I'm still going to start, as we did all of the problems throughout chapters 3 and 4, I always start with my given. And my given in this problem was 1.25 times 10 to the 23rd atoms. And I'm really going to encourage you right now to just get in the habit of putting your substance, because at some point in the future, okay, that's going to become important that you're doing. So I need to use a conversion factor. Where do atoms of magnesium have to go? Well, they're in the numerator here. So that means, remember, I need them to cross out. So atoms of magnesium is going to go in my denominator. And when I look at my tool here, okay, atoms and moles of element. So my other unit's going to be moles of magnesium. Now, what numbers? Notice Avogadro's numbers in front of atoms and 1 is in front of moles. So 1 goes in front of moles and Avogadro's number goes in front of atoms. I'm going to be left with my answer in moles of magnesium, which is what I want. Now, let's talk for a moment about how you put this in your calculator. Okay. So, to put this in my calculator, right, because Avogadro's number is in the denominator, I'm going to divide by it. So remember, I'm going to put this in my calculator as 1.25. I'm going to use that EE button. 23 divided by 6.022 E23. Right? I don't need to put my multiply by 1 in there, right? Because that's not going to change anything. So, now that we've talked about how to put this in your calculator, I'd really encourage you to do that right now and make sure you're able to get your answer. Now, the other thing is, your calculator gives you a big, long decimal number. But we've learned about significant figures, right? So, we need to look at significant figures here. This number has 3 significant figures, and this one kind of really has 4. So my answer should only have 3 significant figures. So I need to write the answer that my calculator gives me, but I need to write it with only 3 significant figures. So you probably should write it as 0.208 moles of magnesium. So hopefully with your calculator you're able to do that. If for some reason you're struggling, that would definitely be a good reason to set up an individual Google Meet with me at some point very soon so that we can work out and make sure you understand maybe what you're doing wrong when you're putting this in your calculator. So this was our first problem example. I'm very particular, okay? On homework, you must show all your work. Not going to give you credit if you don't. And by all your work, I mean you need to show this. Okay? So that's what I want to see on your homework assignments. So the other kind of problem that you can get kind of related to counting is a problem where it's asking you to figure out the number of atoms or ions in a mole of compound. And to do this, you must know how many atoms are in a representative particle of the compound. Now, that sounds like it might be hard, but that's not as hard as you think it is. That is determined by the chemical formula, which is why it is extremely important that you remember how to correctly write chemical formulas given names. For the most part, in Chemistry 1B, you'll be given the name of a compound and asked to write the formula. So remember, our first question when we're asked to write the chemical formula is whether this compound is ionic or molecular. We're going to know it's ionic because it's made of a metal and a nonmetal, or it has a polyatomic ion in it. When it's ionic, remember our process to write our chemical formulas are those 4 steps. We write our symbols, we write our charges, we crisscross down the charges, just the numbers, not the signs, and we make sure it's the lowest whole number ratio. Symbols, charges, crisscross, lowest whole number ratio, that's ionic compounds. If we're given if our question, remember our first question is this ionic or molecular? We're going to know it's a molecular compound, remember, because it's made of 2 nonmetals. Then our prefixes become our subscripts. Molecular compounds, prefixes become subscripts. So, if we look at an example of carbon dioxide, right? Our first question, is this ionic or molecular? It's molecular because it's 2 nonmetals. Carbon and oxygen are both nonmetals. In which case, our prefixes become our subscripts. Carbon doesn't have a prefix, so it's just 1. Oxygen has di, which is 2. And remember, you don't have to have those prefixes memorized. Those are on your helper sheet. So our formula for carbon dioxide is CO2. So, 1, and we would call this a molecule, right? Because this is a molecular compound. And again, our representative particle of a molecular compound is a molecule, right? Molecular compound is a molecule. So 1 molecule of carbon dioxide has how many carbon atoms? Hope you said 1. How many oxygen atoms? Hope you said 2. Therefore, right, 1 molecule of CO2 equals 3 atoms. Right? The 1 carbon and the 2 oxygen makes 3 atoms total. So we know that 1 mole of carbon dioxide is equal to Avogadro's number of molecules. And it has to be molecules because carbon dioxide is a molecular compound. I can't go straight to atoms because it's not an element. And we know that 1 molecule of carbon dioxide is equal to 3 atoms. So let's take a look at an example problem where we're going to use something like this. We're going to be talking about propane is a gas used for cooking and heating. How many atoms are in 2.12 moles of propane, which is C3H8. So again, I like to summarize what it's asking me to do. It's telling me to take 2.12 moles of C3H8 and figure out how many atoms there are in C3H8. So again, I'm going to look at my chemistry toolkit. And one of the things I have to be careful about is I look here and I see, right? I see here moles and atoms. But the problem is, notice my substance is an element. Carbon dioxide or propane's not an element, so I can't use that tool. I can only use that tool if I'm dealing with an element, and this is not it. Because propane's a molecular compound, so this is the tool I have to use. So that means this is going to require multiple steps. So again, I'm going to start with my given. Again, using my chemistry toolkit, I can convert moles of propane to molecules of propane, and it has to be molecules because I'm dealing with a molecular compound, and the smallest piece, the representative particle of my molecular compound, is a molecule. Now, that's a problem, right? Because I want atoms and I have molecules, which means I'm not done. So I'm going to have to use another conversion factor, another tool. Now, molecules are in my numerator, so molecules have to go in my denominator. And I want to convert it to atoms. Now remember, that's what we just did over here, right? We said a molecule of something is this many atoms by counting. So we're going to be able to take molecules to atoms. Now, let's talk about our numbers, right? This is our conversion factor from our toolkit. So from our toolkit, the number in front of moles is 1, and the number in front of molecules is Avogadro's number. Now, in one molecule, how many atoms do I have? Well, one molecule contains 3 carbon atoms, right? 3 carbon atoms and 8 hydrogen atoms. So 8 plus 3, it's 11 atoms in total. So now I'm ready to calculate this using my calculator. Should I multiply or should I divide? I hope you said multiply, right? Because my numbers are in the numerator. So to do this on my calculator, I'm going to take 2.12 times 6.022 E23 times, right? And Usually your times look kind of like this when you type it in your calculator, times 11, and then you're going to hit your enter. And again, we want to kind of pay attention to significant figures, right? So sig figs, we have 3 sig figs here. This has 4 sig figs. And this really kind of is unlimited, right? Because we counted to figure that out. So our answer should have 3 significant figures because remember we're multiplying and dividing, so we're limited by our number that has the fewest, which was 3 significant figures. So you should get about 1.40 times 10. Let me write that times 10 a little bit underneath it. Times 10 to the 25th. And we always need units as well, right? And the unit we're left with is atoms. Now, I'm going to warn you. You have a note quiz eventually over this chapter. And you have a problem on your note quiz that's really similar to this, except instead of asking about total numbers of atoms, it asks about atoms of a particular element. So let's talk for just a moment about how this would be different if instead of just asking for total atoms, what if this had just asked how many atoms of hydrogen there were, right? All that would change, right? I would still go from moles to molecules. All that would change is here, I would say that one molecule has 8 atoms of hydrogen because only 8 of those 11 atoms are hydrogen. Then that would give me how many atoms of hydrogen there are. Okay, so that would be all the difference in calculator wise, right? The only difference would be instead of multiplying by 11, I'd multiply by 8. So it's just kind of a little foreshadowing, if you will, okay, of the fact that you will eventually have a note quiz, and on that note quiz, I ask a problem really similar to this, but instead of asking about total number of atoms, I ask about atoms of a specific element. So that brings us to your homework assignment, which is on page 181, 11, 13, 14. Again, I'm going to reiterate, you need to show all your work. Okay, like this. Again, this is showing all your work. I want to see work like this on your homework assignment. If I do not, I'm going to return it to you ungraded, and you will have to resubmit it showing all your work. And if you don't resubmit it by the 2:30 p.m. deadline, it'll be counted as late. So I'm telling you right now, show all your work when you do it the first time so you don't have to resubmit it. Okay? This will be much easier for you to hand write out. Do not try to type, okay, conversion factor problems. It's a waste of your time. Use that time to do something much more fun than chemistry, please. Okay, so just hand write out your work on a piece of paper, take a picture of it or scan it with the Adobe app, okay, and turn it in for your homework assignment. Have a great day. I'll talk to you tomorrow.